will be a review of terms as well. And if you guys want a copy of this, I don't know that this is on the Canvas thing, but if you do want a copy, just email me. Go ahead, Dave, want a copy of it. But we'll see if what we need there. Where's my got a clicker thing to go forward to somewhere. Oh, well, we'll use it. Okay. So today's loads, right? Things are changing out there, but most are still inductive, right? Because when we're putting a building together, lighting is a huge part of it, right? There's lighting all over the place. We have heating, which can be resistive, but often, do we always use electricity for heat in commercial scenarios? We do sometimes, right? Have you guys put in electric heaters in places? I know sometimes unfinished spaces, or maybe a baseboard heater in a garage room or something. But what's most of our heating fuel? Electric lights is a lot of it, but what do we use for heating mostly? Natural gas, oil. You'll see when I worked at a maintenance, a big facility, we had dual purpose, right? Whatever was cheaper. We'd either feed the boilers with oil or feed them with gas, whatever was cheaper, right? And they paid for them with US dollars or Dogecoin, whatever was cheaper. I don't know it. Okay. But we still have a lot of motors, right? Lights are very efficient. Heat is mostly other fuels. A lot of our electrical load, if we look across the country, is motors, right? Spinning stuff. Whether they're fans, whether they're pumps. Just think of your infrastructure, your sewage system, right? We got these little lift stations, basically pump stations all over the place. Water systems, pumping them up to these tanks so that they can have pressure coming down to us. And those tend to take big loads, right? I don't know, who here has been involved in wiring up motors? You tell me.
I did a pretty cool one over on the 3rd and Lenora building, the one for, I believe it was the negative air pressure fan for that elevator shaft and stairwells.
Yeah.
It was in January, so I'm on the roof, 20 feet up the side of this thing, like hanging off the side of it. Probably should have been tied off, like leaning over, hooking up the motor with the split bolts. A huge pain.
Putting your hand behind the ladder that's welded on there so you don't fall off or something like that.
Yeah, pretty much.
Yeah.
Luckily, it was raining sideways, and I was on the roof of a 30-story building right on the water.
Yeah, that way you can lean into the wind, right? And it's pushing you back straight, so you're okay. Right, but negative air pressure, right? Because we have this concept, right, of when a fire comes on, what dampers open, what close, where do we want it? We want fresh air coming into the stairwell, but we don't want fresh air coming in anywhere else, and whatever you got to do there, okay? So big fans for that. In the bottom of, anybody else, motors? Okay, not so many, that's fine. In the bottom of every building, what do you have in the bottom of your parking garage? You've got a couple of sump pumps, right? Normally 480 volt motors go on, maybe a lot, maybe less, depending what sort of water they have down there, underground pumps going on. In commercial buildings, a little less, but you go to industrial buildings, there's pumps all over the place. Pumps, motors, spinning things, conveyor. You go to the airport, they got conveyor belts all over the place. Get your baggage all around the place. Escalators, keep those running, right? All day long, just keep going. So most of our loads, if we look overall, still most are inductive. And we talk about all these things. Transformers, there's a pro and a con there, depending how we're using them. Lighting ballasts, some of that is changing. This part I want to let us know is changing a little bit. The old lighting ballast, right? You go to your grandparents' place and in the garage, they still got them fat tubes in there and the lights are buzzing. It's probably an old inductive ballast, right? But now what are most of our lights? These are still fluorescent. What are you guys putting in? LEDs. Anybody still putting in fluorescents? Not at all? Okay. A few years ago, we were still putting in a few. Here and there, just certain places, but most of it's going to LED because we can control all kinds of stuff. You can control the color, right? That's a huge thing. Controlling the color of the lighting. Okay. And inductive loads need two types of power, right? An inductive load, like a motor, two types of power. Working power, which is by true power, and the reactive power. We need those magnetic fields, so we can compensate for them. The whole deal. So let's just go down here. Working power, right? That's my watts or kilowatts, and we got to watch out, right? The answer is either 29,000 if it's just watts, or if it's kilowatts, it'd be 29 point whatever, right? So watch out if you're looking for kilowatts or watts. Okay? We have watt meters that will read just the watts. Reactive power. That concept that it doesn't do useful work as we see useful work, heat, light, motion. Circulates between the source and the load. That's that concept that stores it in a magnetic field, and then that magnetic field collapses and it pushes it through, pushes the current through afterward. So just, the main thing is to remember the VARs, the watts. And like I said, if you want a copy of this, just email me and say, PowerPoint slide please, and boom, I'll send it right out to you within a day or so as I get to a computer. And power factor, that's our big thing, power factor. Real work divided by VA, right? We introduced the VA. Because VA is made up of watts and VARs, vectorially. Pure inductor, right? Realistic or theoretical? What do you say, Kevin? Can I have a pure inductor? Yeah. I make a coil of wire, and I got 100 feet of resistance in this one. Yeah, theoretical, but we studied, so it's 90 degrees out. So in reality, this current is not lagging 90 degrees, it's closer to in phase, because every bit of resistance that I add moves it back in phase. But I have, or I can get rid of the inductance, right? Either add resistance or reduce inductance to get it back in phase, lined up. Capacitor, just the opposite. And do you notice this? Both the inductor and the capacitor, what was their power factor? If they were pure, just capacitance, ignore all resistance, power factor was 0, because were there any watts going on in there? Right, we emphasized that last class. No watts, 0 power factor, no real work done. Doesn't matter how much money you throw at it, if no real work is getting it done, your efficiency is 0. The good resistor. All about doing work all the time. It's doing work, whether it's the work you want or not, right? A lot of things put off heat, and that is considered electrically real work. And that's where we use the consumed as opposed to store and release. It consumes or dissipates heat. Phase angle. The more reactance, the bigger the angle. Yeah, because the more reactance, that means if I have reactance, here I have inductive and capacitive reactances, but there's a difference, right? This one's a little shorter than this one, so there's a little bit left over. Big one minus the little one. So I'm left with this much reactance, and that's why we emphasize that total reactance thing. So if I had more total reactance, meaning some of my capacitors burned out and they didn't work as well, I would only be reducing less, and the angle was increased. So the more reactance I have, the bigger the angle. So I put the capacitor to compensate for this to reduce the total reactance. And the more resistance I add, the better the angle, because it's got to go all the way out here, but I'm still just getting into the first floor window. Right? Ladders, we're supposed to have a 4-to-1 ratio on them, but if you've got a 10-foot ladder, and that's all you got, just a fixed 10-foot ladder, if you're going up 6 feet, it'll be like this. If you're going up 9 feet, it'll be like this. Too low, too high, for ratio, but if we get that concept going. That's where we get that 0 to 90. Purely resistive, purely inductive. Purely resistive, purely capacitive. From the reference point, they're either 90 leading or lagging. Let's just talk about the angle. Is that correct? As the angle goes down, power factor increases, right? We're becoming more, what am I becoming? As the angle comes down, Garrett, am I becoming more resistive or more reactive?
Resistive.
More resistive, right? As it comes down, what's happening to my reactance? It's getting shorter and shorter.
Decreasing.
Decreasing, perfect. To find out the angle, remember I wrote that behind the screen here. To find the angle, second function cosine, on your calculator, second function cosine, and then you put the power factor, which is, power factor is watts over VA, that is adjacent over hypotenuse. Okay? The key part here, we're just listing out what they are, and the key is that apparent power is using the total circuits, right? The supply voltage and the total current. The true power is apparent power times cosine theta. There was this question on our test last time on the AC4. True power times cosine theta. Let's put that in terms that we know. What's cosine of theta? If that's the angle, that's this over this, right? Adjacent over hypotenuse. And we know watts over VA to be power factor. So where it says cosine theta, can I put power factor? So can I have true power equals apparent times power factor? We already know this equation, right? Isn't that right? True power over apparent, watts over VA. All I've done is taken the apparent power and put it on that side, right? This is my my algebra. Whatever I do to this side, I do to that. So over here, can I go times VA? As long as I go times VA over there. Those cancel out. So my VA times my power factor equals my watts. So I got watts, apparent, just VA times power factor. Right? That's where I stressed last week before I test, if I know any two of these three, can I figure out the third? Okay. So that's the thing we're getting. Apparent power is total circuit. True power, I can find this way, or I can use the values on the resistor. Someone mentioned that earlier. Measured in watts. Again, we're going through the multiple formulas, and there's even other ones of what power factor is, and those are on our formula sheet. Hopefully we're starting to see the pattern between those along the way. So here's the thing, the higher my power factor, the more efficient my system. Power company likes that. Why does the power company care if I'm more efficient? Using less energy, right? And they're willing to pay me $50 to get a new washing machine, right? Sometimes they have these things. If you get an energy saver washing machine, they'll give you $50, $150, I don't know, whatever it is, your utility, they're changing all the time. Why is that in their interest? Using less energy, they have to build fewer power plants, right? And also, I met a friend at Armistice Cafe in Roosevelt on Saturday afternoon. But there's a new light rail station opening up in October. And what's happening there? They're building apartments all around there, right? As the light rail station's coming in, they're all over that place, right? Up in the neighborhood to be, apparently. And they still have the same power lines coming down the street, right? So if we start building more buildings, bigger buildings in there, then you're thinking maybe the utility has to, CFCD Light has to come in and put additional power poles down there. But if we can be more efficient, can they get the same, can they deliver to a more dense neighborhood with the same power lines? See where I'm going there? That's why the utilities are interested in you being efficient. Okay? Plus, is my electrical system in my little condo parallel to my neighbor? And is my building parallel to the next building? Yeah. So if I have ugly power quality, we'll get into that in fourth year, ugly power quality, does that affect what the utility gives to my neighbor? Because we're all basically, all our residences are in parallel with each other. Nice big web. Okay? So when apparent power is greater than working power, the utility has to supply what? For this motor, I'm getting this amount of horsepower out of the motor, but the utility had to provide however long my hypotenuse is. That's what they got to provide. When they do this, woo, baby, big money. So what are they going to do? They're going to pay the electrician to fix the system, because over time it's going to pay for it. By adding capacitors, you can cut down on this big buck syndrome. And this is a term I like for capacitors. Reactive current generator. Right? The reason I like that term is they're not a generator. I can't just buy a bunch of capacitors and they're just going to run my house, right? No, you need to put energy in. But they provide the reactive current. If I put a capacitor here, the source, if I size it correctly, the source needs to provide the power for the resistive part of the load. But the capacitor, although the source initially charges it up, then the capacitor dances back and forward the power for the inductor. Okay? So it's a reactive current generator. It can work the currents with the reactive portion. It can't help the resistive. It can't do real work, but it can keep your inductors entertained so they're not slowing down the rest of the crew. Right? You got one talker on the crew, can't get rid of them, just hire another talker. Those two will keep each other busy and the rest of you do real work. And if you don't pay either of them, if you can con them into paying each other or something like that, whatever, that's what we're really getting them to do. So my analogy falls apart. Okay. Since they supply less reactive current, if I put one of these in, I love this word, hence, ladies and gentlemen, a smaller bill. Gotta sound like we're highfalutin every once in a while. Poor power factor normally caused by inductance, which is a leading or lagging current for inductors. What do we think of? Eli or ice?
Eli.
Eli, beautiful. Eli, current is lagging. Voltage first, current lags. And we'll discuss it towards the end of the day, why we put them in parallel as opposed to series. There's actually interesting theoretical and practical reasons why we do that. Okay. Utility bills, conductors, fuses, controllers, switches, conduits, right? If all my current in my facility goes down, can I use smaller components along the way? Can I use smaller panels? Can I use smaller wires coming in? Inductors, yeah. This is an interesting one. Capacitors should be disconnected from the line when the devices they correct are turned off. If I have the capacitors that are power factor correcting for this motor, right, I'll throw in all the big words. When I turn the motor off, should I leave the capacitors connected or disconnect them?
Disconnect them.
Disconnect, yeah.
There's electrical potential there, man.
Right.
Feeding.
Right, because if I have a capacitor on, just a capacitor, does it draw current? Yeah, back in AC3, I put a capacitor on the table and we measured it. It drew 1.71 amps, whatever size I had. And it was doing nothing. It was just basically taking those amps, putting them on one side, putting them on the other. Putting them here, putting them here, putting them here. But it drew current. And for those few minutes while I had that connected, the JATC was paying for that power. They were paying just for a capacitor. What was the point? Right? So we want to turn the capacitors off so that they're not wasting power. Okay? And there's actually a code rule on that. Article 460, we don't need, it's not a code test or anything here, but Article 460 deals with capacitors. And there's a couple sections in there. Forgive me, I don't know, it's .6 or .8 or something like that. But there's the under 1,000 volt section and the over 1,000 volt. And it says that when you turn a machine off that has power factor correcting capacitors, within 1 minute, those capacitors have to have their potential reduced to less than 50 volts. Remember my OSHA thing? Less than 50 volts is safer than the rest. And then the over 1,000 volts, you're given 5 minutes to bring it down. That means I shut off all the equipment. By the time I get in there, those capacitors should be dead, or at least less than 50 volts. Remember the safety with capacitors? Those things are a hot potato. Okay? Now this is an interesting one. Capacitors will only correct the power factor from their point of connection in the circuit back toward the source. Here's where I'm going to draw a circuit for us. And I'll draw it back in the way we drew them with RLCs, because this is what we're most familiar with. Oh, put the capacitor there. And we'll put the motor here. We'll just put it as a pure inductor for right now, because we'll get into the difference later. Right now, if I have no capacitor, I have an RL circuit, right? And the currents are going to be this way, and I'm going to have a total current like that. But if I put an inductor, yes, purely inductive. But if I put a capacitor in here, then I add this, and I get to cancel out those two, and all I'm left with is this. This thing goes away. Is that correct? You should be fairly familiar with that concept. But what happens if this is 10 amps, and this is 10 amps, and this is 10 amps? How many does the source have to provide here? Just the 10. Because are these 10 just going back and forward? Yeah, it's at resonance. These 10 are going back and forward, so the source only needs to provide for the resistor. So how many amps are flowing right here? Right here. The source is providing 10 for this. There's 10 here going back and forward, right? Because these 10 amps are going back and forward. If they're equally balanced, do they need the circuit to kick in anything? No, just when I turn it on, it charges it up, and then these two dance perfectly. That makes sense why I got 0 here? Make sure we're good there. And here I've got 10. It will always need to provide for the resistor. I can change the size of the capacitor to bigger or smaller, right? And it may need to kick in the difference. But here's the key. If this section is 0 amps, does it make a difference where I put this capacitor? If I put the capacitor here, there's 0 amps for a short period of time and 10 amps for a long period. But if I put the capacitor over here close to the motor, did I have 0 amps all the way out to get right close to it? Yeah. Let's get rid of that picture. That's why we started going with how many amps where in the circuit. So let's just draw it this way. Motor, panel, conductor is going out to the motor. The motor is always going to get its full current, reactive and resistive. Resistive from the source, reactive from the capacitor. So if I put the capacitor back here, would this wire be getting the full amperage of the motor or just part of it if I put the capacitor at the panel? The full, yeah, wouldn't the motor be drawing the full amount? Yeah. But if I put the capacitor here, this little bit of wire would still have the full current, but would it be corrected back here? Would this be the reduced part? Yeah. This part of the wire would only be carrying it for the resistor, whereas here is the resistor and the inductor. So do you see where it makes a difference where that is? So if I have less amperage back here, my terminations are cooler, right? What's a weak spot when we're putting wires together is our terminations. Normally it's not the wire in the conduit. Normally that just sits there and does its thing, unless it's been damaged in the process, right? You're pulling it across and someone's driving forklifts over it as you're pulling the wire before you put it in, and we're gonna have a problem, right? Try to keep it out of that pathway.
So they just build the capacitor kind of into the motor as part of the unit?
So it depends, right? And I'm not gonna get us confused with VFDs, it's that they're more internally taken care of, okay? But when I dealt with capacitors, we had motor control centers. So what we had is we had a panel that went to, so I'll get rid of this, right? The motor still has resistive and inductive. And we had what we call an MCC, the motor control center, and it had a whole bunch of different divisions in it, right? The power came in and went into different busing, and then it went from here to different motors all around the place, right? It went to a bunch of different motors. But let's say for this one that goes in here, taps off the bus, goes through, has all its little controlling stuff in here, then we had these little capacitors down in the bottom of here, in part of the motor control center. So the full amperage of the wire went in this last section, but coming in to the motor control center was power factor corrected. So that was where we had them because they fit well here. And by code rules, you cannot reduce the size of the branch circuit wire for having a capacitor in it, even if I put the capacitor right here. What's my branch circuit? What's the definition of branch circuit? You remember that? After the last, yeah, I'm gonna be more specific, overcurrent device. Right, after the last overcurrent device. So the code says I cannot reduce the size of the wiring, the branch circuit, even if the capacitor is right out here. And the reason for that, well, what if my capacitor goes dead on me, doesn't work anymore? That's part of the reason, right? But feeders, panels, service conductors, that can all be reduced in size. So if I can have a 400 amp panel instead of an 800 amp panel, that's big money savings at all kinds of levels, right? And plus, if I have less current, even if I'm in a branch circuit where I'm using full-size conductors, the more length of conductor and the more terminations where I have a smaller amperage, the cooler the temperature of those terminations, right? If terminations get loose and stuff like that, that's our weak spot, is our terminations. That's why the code is very specific on those, okay? But the point we're trying to make is, do you see how a capacitor makes a difference where it is in the circuit? Because, I think it's on the next slide, the capacitors can be placed anywhere after the metering equipment. Let's say my service to the building comes in here. I could put it right here, right after the power meter for the utility, because I can get an average of all my loads out there, right? I've got resistive, inductive, capacitive. Some of them kind of correct each other, working back to me here. And if I correct them here, I just pay the bill for what I'm using, for the real work being done, and I look really clean to the utility. And it's actually cheaper to do it here, because everything takes care of itself, and I just put in one capacitor bank right here, easy, it's done. But everything from here on is taking full amperage. Is that correct? I only corrected it from here going back to the utility. Everything in my facility needs to be full-size wires, feeders, panels, transformers, everything. Now, so that's cheaper, but the least benefit. If I put them all right next to every motor, would that be the most benefit? Yeah. Don't worry about the cost. We're just worried about the most benefit if I put them right by the motors. But sometimes that costs money, right? So then the accountants get involved and the business owner gets involved, sees how soon he's going to have to start paying kids tuition, and he goes from there, right? But they decide, do I want them in the service? Do I want them along the way? Do I want to buy the last motors? Where do I want them? And there's a cost-benefit analysis done to that. So let's think of the airport. I had a bunch of work out at the airport, and over the years, even before I was in Detroit, I threw bags for a while. And they have hundreds of motors, if not thousands, right, of 1 to 10 horsepower motors running those little conveyor belts all over the place. From a maintenance standpoint, would it make more sense to have a capacitor by every single motor perfectly sized? They're not going to put one way out of the source. Or how about if they go to the electrical room and say, this panel just deals with a bunch of motors? Could I put a capacitor bank by that panel? Then I don't have a whole bunch of them all over the place, and I gotta send a maintenance guy all over the place looking at them all the time. You see where I'm going with this? So they decided that we'll lose some of the benefit, but it's easier for us here. So they have a capacitor bank, and what's happening to those motors at the airport? Are they turning on and off all the time? Right, they're on, they're off, right? No bags are on there, the things turn off, they've all got these little electronic eyes, all that sort of stuff. Push buttons, turn it on, but it goes for 3 minutes unless the eyes keep seeing action, whatever it is, right? So, what's that thing doing? As the motors are turning on and off, is my power factor changing all over the place? Right, it's moving around the place. So, when the angle gets too big, they turn on more capacitors, bring it back down. Then the motors get turned off, we're getting too close here, we don't want to go the wrong way, so then they turn off some of the capacitors. Do you see what they're doing? They're just kind of keeping it in a range, like this. Same thing your house thermometer does, right? Keeping your temperature in a range. You put it at 62 degrees and it may say 63 to 64, you know, whatever it does. It turns on the heater, off the heater, as needed. If it gets too hot, it turns on the air conditioner. Right, you with me there? So that's where they do it. But do you see how we get the most benefit here? But it's the cheapest cost way at the back. Where do we end up doing it? Key point there. So lowest installation cost right after the meter. That means we're all good for the utility. No penalties. It's big money. Okay? Most logical location would be at the most logical for the highest benefit would be right at the motor or point of consumption. There we go, for maximum benefit. But sometimes we meet in the middle. This one we've already gone through, right? VARs. We can figure out the VA. How can I figure out the VA, George? If I have horsepower and I know the volts and amps and all that, I have horsepower and I have volts and amps, how am I going to figure out the VA of the, what numbers am I going to use for VA?
You can use the Pythagorean theorem.
Okay, but if I don't know any of these others yet,
Oh,
but I have some of the numbers that deal with the motor, the volts, the amps, and the horsepower, what am I using for VA? Feel free to look over there.
I mean, if it's three-phase, you can go voltage times current times 1.73.
Perfect. And that gives me what I'm putting in, right? If it's 480 volts and it's drawing 45 amps, 480 volts times 45 amps times 173. Single phase, I just don't use that part, right? That's how I get my VA. How about my watts, James? What am I gonna use to get my watts if I just have the motor nameplate?
Your horsepower rating.
Horsepower, because 1 horsepower is 746 watts. Beautiful. Okay? Excellent. And then they have this other equation. We can do tangent to find this, is the way this goes. You can also use the Pythagoras that George was talking about. If I know any two sides, I can figure out the third one, Pythagoras. Right? Trig was all a matter of if I know an angle on one side, I can figure out all the rest and get all excited. Okay. So, we're going to take a wee break, and then we're going to come back and we're just going to solve this problem. And I believe this is the one out of the